Okay, so we're going to make this start. As you are observing from the video sequence, we're breaking this chapter up into two parts. This will be the second part of chapter 22. We wanted to dive a little deeper now into how charge separation works within an atom or within a molecule. So we have a picture here of an atom with a positive nucleus and in a cloud or circulating bunch of electrons. Obviously, there aren't as many electrons as are shown here in dots, so it's just a schematic of a multi-electron atom. In a charge polarization event, what happens is one side of the atom or molecule is induced into becoming more negative or positive than the other side. At that point, the atom is said to be electrically polarized. We could do that, for example, which was one of the examples we had earlier, but I'll try to briefly review it for you. If I imagine in object B right here, where you see that the electrons are actually moving more to the left. They're no longer centered on the positive charge. So there's an external force involved that is forcing the electrons to move away from the right side of the atom. And that could be the existence of other negative charges over here. If this was an atom in the wall of a building structure and the balloon, which we said was negatively charged, was placed over here, then the electrons from the atoms on the surface of the wall would be pushed away. And that produces a charge polarization. Now, we have not removed electrons from the atom. The electrons are just as many electrons are still there. We haven't rubbed any off, but they've been dislocated from their ideal site and moved further to the left. The center of the negative charge cloud normally corresponds with the center of the nucleus, which is where you see even distributions on the right and left side, up and down, of all the electrons. But the external negative charge brought by nearby on the right side in figure B has pushed the electrons to the other side. The atom is now electrically polarized, and that's how we get polarization. If a charged rod is negative, then the positive part of the atom or molecule is tugged in a direction towards the rod. So imagine again that this blue area over here is composing the wall of a building. And this, which was previously shown as a balloon, is just a negative rod. As it's brought near to the wall, the electrons in the atoms of the wall are repelled and displaced away from the central positive nucleus of the atom. And so there's much more attraction between the negative and positives here, because the positives are closer to the negative on the rod than the negatives are, which are located further away. Furthermore, the negative and positives cancel each other out in this middle column over here. So the positive and negative pairs of the atoms and molecules become aligned, and they are electrically polarized because we have a direction of polarization towards the rod that is inducing the charges on the wall, which is, of course, due to the electrons being pushed away. So, by the way, the positive charges are not mobile. They are to be viewed more as fixed objects, and it's the electrons that have greater mobility because they're 2,000 times lighter and easier to move than the nucleus. In the case that we talked about before, the case of rubbing two objects together, well, this is a case not of rubbing, but we could suppose that we've already created a cone with a net positive charge on it. So electrons have been pulled away off of the cone with another object that's been rubbing against it. And when the charged cone is brought near a small piece of paper, the molecules in the paper become polarized as well. So in this case, the electrons in the paper are attracted towards the cone. That leaves the far side on a more positive net charge. The closer side is negatively charged, and the dominant force is going to be between charges that are closer together. So the net effect is that even though there is a positive pull of the paper towards the comb on the near side, which are where the charges are closer together, there will be a weaker repulsion force because the positives on the comb are further away from the positives on the paper. So the net effect is that this F minus force is stronger than the F plus force because the distance between the charges is smaller and therefore the strength of the force is larger. This is the same effect that we talked about before, that rubbing an inflated balloon on your hair, but now we can understand it in terms of what happens with the polarization of the molecules in the wall. So what happens is that when we charge the balloon negatively by rubbing it against our hair, we remove electrons from our hair onto the balloon. When the balloon is placed near the wall, then it pushes the electrons away from their atoms that they're originally located with, and therefore the closeness of the negative and positive charges causes a stronger attraction than the repulsion from the electrons, which are further away. Again, closeness wins. In other words, the charges, forces that are most responsible are the ones that are closest together. So here the negative and positive will attract much more strongly than the negatives on the balloon will repel because of the greater distance. Now there are some molecules that are naturally polarized. They don't need an external force or an external rod to polarize them, or an external charged object to polarize them. One of these is our familiar molecule H2O. We've shown here pictorially kind of a Mickey Mouse cartoon figure where the central light blue area is the oxygen. So in the center of this blob is the oxygen nucleus that has 8 protons and 8 neutrons. And the hydrogen only has 1 proton and 1 electron. Now, because of the fact that there's greater affinity for the electrons to the positive center of the oxygen, the electron spends much more time going around inside the region of the oxygen, leaving a deficiency of electron around the proton, then begins to look sort of like a free charge plus charge particle because its electron has been gobbled up or absorbed in or spends more time in the vicinity of the oxygen atom. And so we get a distribution of electric charge that is not really symmetric. In other words, there's a polarization in the water even though there's nothing there to generate that. And such molecules are called dipolar or having what we call electric dipoles, or simply dipolar molecules. Now, up till now we've only talked about forces. Forces are how many newtons is exerted between 2 charges that are attracted towards each other. There's another important quantity which we call the electric field. And the electric field is a quantity that surrounds exists in the space surrounding the electric charge, and it is due to the electric charge in the middle that is causing the attraction. The unit the way we quantify this is to say that a single charge by itself can generate a force field. And if another charge comes in the vicinity of this negative charge in the center, say off at some distance radially away, then if it is a positive charge, like a proton, it will be sucked in with the arrows directed inward. And the force on the particle sitting at some distance away will be radially inward, and that will be the direction in which the charge will fall. So one way we quantify this, of what we call the electric field, is to say that I measure the force between 2 charges, which is this negative charge and my test charge off at some distance away, and the field that is only due to the inner charge, negative charge itself, is the force of attraction divided by the force of the test charge out here. So I have a test charge out here that's attracted to the central charge here, but when I take that force and divide it by the charge of the object, I get a property that only depends on the negative charge. It doesn't depend on what else is out there pulling it in. It is a unit called force per unit charge, and it is unique to the object that has a charge. It doesn't depend on the other object that it is tugging on. We're familiar with this from Star Wars. When the Star Trek enters into a high field, we call it it's experiencing a high gravitational field. A high force field means that there's some object outside of the spaceship that's causing a huge attraction. It's a property of that matter that's pulling on the spaceship, which is usually gravity in the case that we're discussing, but it's only the gravity due to the mass of the star or object that's pulling the spaceship into it. And we get that principle of a field or force field as due only to the object that's sucking things in. It doesn't depend on the object that's being tugged on or experienced. But we can calculate it once we know the force per unit charge. I can tell you if I put 2 coulombs of charge out here, I multiply that by the electric field, force per unit charge, and I get the net force. So force per unit charge times charge will give me the force, and I can calculate things from that. Now, electric field direction. The electric field has a direction. It is the same direction as the force on a positive charge, and it will be opposite in direction to the force on an electron, which has negative charge. In this case, if I have a positive charge that is generating the field, the force field, then those field lines will be radially pointing outward because any other positive charge located around it will experience a radial motion forcing it away, and that would be an outward radial force. On the other hand, if I place an electron in some distance from the positive charge, its force will be opposite the direction of the field because the electron will be attracted and pulled inward, whereas the field of the positive charge is always radially outward because it is defined by the force on a positive charge. Another interesting example of distributing charge by contact is by what's used as a high voltage Van de Graaff generator. This lady here is standing on a platform that isolates her from touching any nearby metal to keep her from getting electrocuted. She is isolated with an insulator, a material that keeps her away from any electrons coming from the ground. And because the generator itself is generating a huge electric charge on the surface of this sphere, which in this case we will look at as a negatively charged dome, then by touching it, some of those electrons are traveling into her body and reach her hair, distributed everywhere. The electrons try to move away from each other as much as possible because they repel each other. So they will move to all parts of her body. Some of that charge will go to her hair, but each strand of hair will have part of that negative charge. So every strand of hair becomes negatively charged, and therefore 2 strands of hair will repel each other, and that makes her hair stand up in the way that you see here from a Van de Graaff generator. So this is a case of charging by contact. The girl is getting charged by contact, physical contact, with the charged dome of the generator. We finally come in this chapter to the idea of electrical potential, or what we call electric potential energy. And actually they're slightly different. I shouldn't be quite so cavalier about it. We'll talk about electric potential energy first. The energy possessed by a charged particle due to its location in the field is a measure of its electrical potential energy. And the basic idea is that if I imagine that I pull this rope, I have a negative charge here, which is the source of attraction. And I have another mass which has the opposite charge, which is positive. And initially it's sitting out here very close to the green sphere, which is negative. If I pull on the rope with a pulley, I have to do work not only because of gravity to pull this charge up by a distance away, but I have to overcome the force that's pulling it towards the center by virtue of its charge. In fact, this whole experiment could be done in free space where there's no gravity at all. In the absence of gravity, I would still have to do work to pull the positive charge up. And when I do that, I create potential energy, because if I release the charge, it will be attracted and come right back into the negative charged sphere. Now this could be done from any angle. If I'm doing this in free space, in a spaceship where there is no gravity, then up and down makes no difference at all. The only force is the electric force, and gravity is nowhere to be found in the equation. So the only thing pulling it back down is the electric force. So this is very similar to gravitational potential that we talked about, where if we lift up a massive object by pulling on the rope on a pulley, and we raise it a distance of height of 1 meter, for example, and it has a certain mass, which we'll say was 1 kilogram, then the potential energy is going to be what we call mgh, mass times the acceleration of gravity times the height. So if this was a 1 kilogram mass and we raised it 1 meter, then it would be 1 meter times 1 kilogram times 10 meter per second squared on acceleration. And so it would increase its potential energy by a number numerically equal to 10 joules. On the other hand, if we now cut the rope, that potential energy gets translated back into kinetic energy, and the amount of potential energy lost when it comes down is equal to the kinetic energy gain. And the same thing works with charged systems as well. So that's potential energy. And the potential energy is equal to the work that we have to do to separate the charges over a given distance. Another example of electrical potential that has a mechanical analogy is that the spring has more potential energy when it's compressed, because if I put an object on the end of that spring and I release my hand, that object will accelerate with the force of the spring pushing it out. The potential energy when the spring is released becomes kinetic energy of the object when it's accelerated when the hand is removed, assuming that the experimenter has a ball that is connected to the end of the spring that will accelerate it. In the case of the charged particle, we are doing the same thing as compressing the spring, if in fact the two charges are positive, because now the positive charges want to push against each other, so I have to apply a force pushing it towards the center of the sphere, which will increase its potential energy, because when I release it, it will be forced with the force of the electric force will accelerate it and cause it to move outwards. So in both cases, the increased potential energy by pushing them closer or shoving it in is the result of doing work, and when I release that pressure or that force by hand, then that potential energy is converted to kinetic energy as the particle accelerates away back outwards. So now we come to the idea of electrical potential. Up till now we've talked about electrical potential energy, which is the analogy of mgh was the mass times g times h was the gravitational potential. The electrical potential was the potential energy by removing or displacing the object against the force field. And again, that's against the force field, so that when I release it, it's attracted back towards the direction of the forces being applied. But if we divide that potential energy by the amount of charge, that is called voltage. And the voltage is a unit of electrical potential. But the idea of a volt is its potential energy per unit of charge. It's a little bit of an abstract one. It's a little bit hard for me to describe in a more intuitive way, but the important point is that if I increase the potential energy by pushing the positive charge towards another positive charge, divide that by the charge of the object I'm pushing, that would what would be called the voltage. And the voltage is strictly a property of the charge that is doing the work, which in this case is the large sphere here. The large sphere is the one that's actually doing work on this positive charged particle when I release it, causing it to accelerate outward. And so that's the idea of electric potential. It is the amount of electrical potential energy divided by the charge of the object whose energy is being increased by moving it. So unit of measurement is the volt. We haven't really talked a lot about the unit of charge, which is the coulomb. We'll come back to that in a minute. But knowing that we have a unit of charge that we can measure, the volt is defined as the amount of work I do on a charge divided by the charge itself. That tells me it's a property only of the source that's forcing me to do work to increase the potential energy of the object that I am moving from one point location to another. If I have twice the charge in the same location, then it will have twice the electric potential energy, but it will have the same electric potential. In other words, If my test charge over here has twice as much charge in the lower case than in the upper case, then there will be twice as much force or potential energy required to move it in the force field, move it closer. But if I divide it by the charge of the object, then the force per unit charge will be the same, or the joules per unit charge will be the same for both of those objects. So if I have 3 times the charge in the same location, it will have 3 times the electric potential energy, but the same electric potential. So electric potential is the voltage, and it's describing the amount of pressure or force that it can exert on a nearby object without actually telling us how much charge that nearby object has. And so we call that a joule per coulomb. High voltage can occur at low electrical potential energy for a small amount of charge. It can occur at high electric potential energy, and will occur for a large amount of charge. Here's a question for you. Electric potential energy is measured in joules. Electric potential is measured in joules per coulomb, referring to the same object. Joules is the work done on that charged object. Joules per coulomb is the work done on the object divided by its charge. And that is called electric potential, and that has units of, we said before, is units of volts.